Hey everybody, this is Alex Merced from alexmercedcoder.com. Make sure to like this video, subscribe to the channel if you haven't already, and subscribe to my podcast on iTunes or Spotify by looking up Web Dev 101 or Data Nation, my two podcasts. Now, in this video, what I want to do is just kind of go over the fundamentals of computer science. It's just like understanding like how the computer is working to kind of really appreciate sort of like what programming languages are doing for us and why things like data structures matter and whatnot. At the end of the day, like the way the computer is fundamentally working is all literally through electrical impulses and electricity is either running or it's not running, it's on or off. Okay, so that's kind of like a 0 or a 1. Okay, so if I were to just drag some text over here. Okay, so essentially, like if the electricity is off, that's a 0, and if the electricity is on, that's 1. Okay, so that can be treated as like a true or false, or a yes or no. With that, we can count in what's called base 2. Now, what's base mean? Okay, so let's just get this concept across. Now, our normal everyday counting, the way we generally think about numbers is in what's called base 10. Okay, which means, we go 1, then 2, then 3, then 4, then 5, then 6, then 7, then 8, then 9. And whenever you hit the 10, okay, you move on to another digit, okay, and then you'd be like 20, 30, 40, 50, 60, 70, 80, 90, and then once you hit 10 again, you go on to the next digit, okay? So basically that's how we all think about numbers in this base 10 method. There are times where you use like other types. So when you hear people talk about like base 64, base 2, it just means like how many things till you move on to the next digit, till you go on to like the next column. Okay, so like that's why when you see like hex color codes, you'll see like FF is really because they're using I think like base 16. So technically, you go past 9, so then you start using letters till you get to F. So like technically like 9, and then I think A is 10, then B is 11, and so forth. Okay, so now you understand what that terminology means. So since we only have 0 and 1, because the light's either on or off, okay, you can count technically in base 2. So it would be like 0, 1, and then this would be technically 2, right? Because we're moving every base 2, every time we hit 2, we go on to the next column. So this would be 3, and then this would be 4. Actually, no, that would go here. 1, 0, 0. This would be 4. Okay, just to kind of get the idea of how that works. So essentially, we have to represent like every token, everything as a base 2 number because the electricity is either on or it's off, right? Okay, so we have to express everything in base 2. So that's where you get like binary from. So when you start seeing like 0, 0, 0, 0, 1, 0, 0, 0, 0, okay, you're basically saying, electricity on, electricity off, electricity on, electricity off, and that's gonna total up to a number. Okay, now, so literally all that's going on is your processor is receiving a bunch of electrical impulses, kind of like Morse code. That's kind of like on or off, on or off, on off, on off, and then it's interpreting it. The question is like, at what point do we treat something as sort of like one letter? Okay, where does one letter end? Where does one idea end? This is where you start hearing the concept of like 8-bit, 16-bit, 32-bit, 64-bit. The idea is like how many bits can sort of one thing take. So one bit, if I remember right, like I think 1 bit is just like basically one of these 1 or zeros. Okay, so the idea is that so 8-bit, basically you would have to represent everything in 8 bits. Okay, so essentially like every letter, every number, everything you plan on doing has to be done in this many characters. Okay, you don't get any more than that. So then what's possible? So let's see here, like what's the maximum 8-bit integer? That's how we can know. That's how we'll Google this. 256. So basically, if you're limited to 8 bits for sort of one granular piece, that means you can only have 256 sort of possible things you can represent. Okay, you only have 256 possible values. And you have to then write all your hardware to be able to interpret those 256 values in different ways. Okay, so basically, like the graphics card in your Nintendo, there's only 256 possible values because, again, 8 bits. You can only rearrange those zeros and ones in 256 unique ways. That you were very limited. So this is why, like, when you get to like 16-bit consoles, like things get looking a little nicer, and you get to 32-bit, they look nicer, and 64-bit, they look nicer. Basically, every time that doubles, basically you have that many more possible values, which means the possibility of what you can express is greater. So that's because at the end of the day, it's just zeros and ones. It's all on or off electricity switches. Okay, so that's all it is. So there's basically, really, what we can do is really all the computer can do at 8 bits is express 0 through 255. That's in basically the graphics card has to take that 0 through 255 and figure out how to make that into, interpret that to put colors on a screen. A controller has to figure out how to interpret that 0 through 255 to respond to commands and so forth. Okay, so that's where that kind of comes in. Okay, so now we live in a world where basically that's not as much of an issue. So right now we use far as like what different letters mean, okay, we use a system called UTF-8. Okay, so this is like the binary for, like, if I go, let's take a look at like a UTF-8 chart. Do we have a UTF-8 reference? See if I can find an example in binary. UTF-8 binary code. Okay. So let's see here. Let's take the letter A. Okay, and see, that's what it looks like in binary. So like the letter A is that. Okay, but the thing with UTF-8, because we have so many more bits available to represent one letter. Okay, you have more room to have lots of possible. And as far as like how that works, I really recommend watching this video. So if you go to YouTube, there's a really good video that explains like this character set deal and why it's so important. YouTube.com, the UTF-8 miracle. So good. I highly recommend watching it. Okay, there it's broken down really well so you can understand sort of like why. So now computers can express more things because, again, you have higher bit processors that can process more bits at the same time to process more complex ideas. Okay, and that's essentially what's happening. At the end of the day, everything is just zeros and zeros and ones. Now the thing is that, like, if you and I had to write code in zeros and ones, that would be quite torturous to sit there and literally have to like write a bunch of 0 and 1s to get the letter A, and then a bunch of zeros and 1s to write the letter B. So what generally you do when something is complex and tedious, you create what's called an abstraction. An abstraction is something that simplifies it, gives you sort of something that's easier to use to do the same thing. So the processors came out with a language called assembly, but there's different types of processors. So each processor had a different sort of version of this assembly language. Okay, and if we take a look at what like assembly looks like, okay, it looks like something like this. Okay, still looks pretty nonsensical. It looks like a lot of gibberish, but a lot better than zeros and ones because now you have like these little abbreviations, and really what you're doing is you're still, and here's like a good example of what it's doing. Essentially, what you're doing is you're just like moving data from like a piece of memory to somewhere else, and that's essentially what it's doing. So you're saying, hey, make a string here, move it there, add this. It's pretty. It's not that much of an abstraction, but it's enough to make it easier to write code for that processor. Okay, so essentially the processor reads this, and the processor knows how the assembly language for that processor, and translates it to the zeros and ones, so that we can run the actual program. Because at the end of the day, the computer, electricity is just on or off. So it has to take these instructions and then translate them into those electrical impulses, so that way all the hardware can then do what it's supposed to do, like respond to it. Okay, because literally at the end of the day, like your keyboard, all it's doing is just receiving those little zeros and ones from your computer, and it just knows how to respond to the right combination of characters. Okay, that's really all that's happening. So you're just sending these expressions in zeros and ones to different hardware, and they know how to respond. Your monitor is being sent a chain of zeros and ones, and based on the zeros and ones it's receiving, it knows which colors to put on what parts of the screen. Okay, and we'll get into like how that all happens. But again, we're just building up to like how the whole computer works. Okay, so the problem is like you have your AMD processors, your Intel processors, your ARM processors, and each category of processor has their sort of own way of doing assembly. They're most part the same, but there's still enough differences that you can't just sit there and say, hey, here's a program I wrote for the Intel assembly language for an Intel processor, and just say, hey, I'm going to run it on an AMD processor. So you still need another level of abstraction. So that's where like C++ and C come along. So when you take a look at like C, and so these are, and every time we make an abstraction, that's considered going higher level. So relative to assembly, C is what's called a higher level language. But relative to like Python and JavaScript, C is a lower level language, because you'll see like Python and JavaScript are much higher level abstractions. Okay, so we would take a look at C code, just so you can see what it looks like. Okay, here we go. So here's like C code, and now we're starting to get to something that looks a little bit more like English. Like we can kind of see what's going on here. I can say, okay, this is the main function, and we're going to print this text. We're declaring some individual character variables. So these are like pointers to a chain of characters, and that's all good. We're printing some more stuff to the console. Okay, and yeah, I can now we're getting to the point where we're writing code that I can now more easily read and understand as a human. And essentially what happens is that when you take C or C++ code, you run that, but the computer has no idea what this means. It doesn't. It only understands zeros and ones. So essentially what happens is that compiler, okay, that compiler can then compile it to the assembly language for your target. So if you want to compile for Intel, you want to compile for AMD, you want to compile for ARM, it'll then compile it to the right assembly, and then the processor can then translate that assembly to the binary. Okay, so just to kind of see like the steps in between. So again, all these abstractions, we just keep compiling to the next level. And then you start getting to the higher level languages like Python, JavaScript, whatnot. And what they do is they take a lot of the difficulties, a lot of the things you'd have to do over and over again in C++ or C, take those out of the equation so that way you don't have to worry about those things. There's always costs and benefits. Of course, like when you try to create an abstraction, there's certain things you have to assume about the people who are using your abstraction, which usually is a trade-off of speed, because you have to do things in less efficient ways to make sure it applies to more situations. Okay, you could write the fastest program in the world if you just did it in binary, but it would take you years. I can write a program pretty fast in Python and JavaScript, but it's not going to be as fast as the one that was written in pure binary, because that's going to be the most efficient use of space, because you're not doing anything extra. But Python and JavaScript, they are interpreted languages, and really what's happening there is that they're being interpreted on the fly and being turned into, sometimes depending on the language, interpreted into like C++, which then gets interpreted into assembly. Like it makes its way down, but it makes a lot more assumptions for you. There's a lot less that you have control over, so that way you can do the things you really want to do faster. Okay, so just so you can see, like at the end of the day, it's all zeros and ones. Okay, and all these languages these are just abstractions to make it easier to feed those zeros and ones to your computers in a sensical way. Now, how does your computer know how to talk to your printer or your keyboard or whatnot? They use things called drivers. Okay, and then drivers are just basically pieces of software that say, okay, these are the, this is how you communicate with my keyboard. Because bottom line, like there's a hardware interface, like the physical like thing that you plug into your computer, which then receives electrical signals. Okay, and the question is like, you might be receiving like 0011111111. Like basically, you left click on your mouse. What is the computer? What electronic signal is the mouse sending to your computer, and how is that interpreted? So for all I know, the electrical signal that might be sent by me left clicking might be the equivalent of A on the keyboard. But the mouse's driver, the software program for the mouse, knows that when they receive like that signal of A, to do what a left click does for that mouse and whatnot. Okay, so you're reusing the same signals for different hardware, but different hardware responds to those signals in different ways, and that's what the drivers do. They say, okay, when these signals come in based on whatever is sending in the signals, whether it's another program or hardware like your mouse and keyboard or a gamepad, how do we treat those signals coming in? Okay, and again, different drivers have to be written for different operating systems. So like nowadays, you never really think about drivers anymore because most computers are connected to the internet. So either your operating system already has a driver built into it that can communicate with most hardware. So most hardware is plug and play, especially now that everything is more standard. So instead of everybody having their own different version of a mouse driver and a keyboard driver, there's more standards on like, okay, this is the standard keyboard driver that should work with most keyboards. As long as you build your hardware to follow the standard, it should just work. And that a lot of standardization in computers has come today, because before, companies wanted to make sure that you could only use their thing, so everyone would come up with their own version that was different, but then it was like torture for consumers, and that wasn't good for business as well. So eventually everyone kind of converged on setting standards, like standard ways to create drivers, standards in operating systems, standards of how we communicate between computers. So that way us as users are more happy to use computers because we don't have to think about all this, because most things are going to work the same, and everybody knows what those standards are, and those standards are programmed into the software we use. And even as developers, we don't have to think about them a lot because, again, a lot of those standards are built into the libraries we use. Okay, but again, understanding that helps you kind of appreciate, like, even if there's not like a clear way of doing something, you can probably figure it out. You just kind of have to figure out sort of like how are these things fundamentally communicating with each other, and just send the right signals to the right places in some way. Yeah. So that's kind of like how the computer works and interprets the text you do. But at the end of the day, like going forward, like we have all these zeros and ones. You have your processor. Okay, your processor, which is a part of your computer that interprets these signals. It's basically the one that like grabs all these signals and then translates them, so that way like the process, so like whether your computer knows what to do with them. But the thing is, you can't look at everything at the same time. So when you load up a program, there's going to be stuff that's like, there's got to be a place to store stuff while you're executing it, and that's memory. Okay, and this is like when you have like let's say like a 16 gigabit RAM. The processors, when you might hear like it says, like, say, hey, it's 3 gigahertz. Okay, and let me just. Okay, and let me actually put the labels here again. Processor. That's why you can't really hit image on this Lucy charts. So processor and RAM. Oh, which is memory. Okay, and then the thing is that like everything on your computer isn't running all the time, and sometimes your computer's off, so you need somewhere to store stuff when you're not using it, and that's what your hard drive is for, which may be even bigger. Okay, so then here's like your hard drive, which may be like, let's say 2 terabytes. So oftentimes, if I open up a program, that program is stored somewhere in my hard drive, but the first thing that it does, it's going to go grab the information for that program to run, move it to the memory, and then the processor begins processing it from memory. Because the way memory is created, random access memory, it's created in a way that you can access the data a lot faster. Because hard drives, not so much anymore because you have solid state drives, but traditionally, what hard drives, the way they worked is they were like a spinning disk that you would like write to. So like you would have to like wait for that spinning disk to spin many times to get all the data. So if you were actually running the program from that, it would be really, really, really slow because you're having to wait for that disk to spin. So that's only to initially load the data. Once the data is in memory, that's when the program runs. The memory is really fast, and actually the physical memory chip is generally located pretty close to the processor. And even the processor generally has like its own like cache. It might have like a, let's say like 3 megabit cache. Processor 3 gigahertz with like 3M cache or something, we'll say. And we'll just say 8 megabyte cache. It's just a little bit of space. And that little bit of space, it can then save like its most immediate things to process things even faster there. Because again, and that's like the big thing with like ARM chips, that they kind of combine the memory and the processor into one big chip. So that way, the downside is you can't upgrade it, but the bright side is like it's much faster because the memory's right where the processor is, instead of them being two separate things physically. So again, there's like the physical aspects of like, data's got to travel from here to here, and then this has got to process it. And then there's a whole bunch of like, how did you organize the data here? And how fast you organize the data here can determine how fast a processor can do certain jobs. Okay, because you might have organized it in a way that's going to has to do more stuff to get to the same place. So this is why you think about like data structures and algorithms, because you're trying to think, okay, how can I use up the least amount of memory and do it where there's the least amount of steps, so that way I can have more memory, so that way I can run more programs at the same time, and it's efficient as possible. It does less things, so that way the processor can process it faster. Okay, because again, all this has got to be like physically like done by the computer. And last, nowadays processors don't get much faster. Like 3 gigahertz, you're not really seeing like 4 or 5 gigahertz. So how do computers continue to get faster? What happens now, you're starting to see like 2-core, like 2 cores, 4 cores. Now, what does this mean? Think of the core as like the actual processor brain. That's actually running so like just a normal processor will have 1 core, so you'll have one thing that's processing data at the speed of 3 gigahertz. Okay, and that's the speed that it's running through these directions. But if you have 4 cores, now you have 4 brains that can take 4 simultaneous instructions. Okay, and that's how processors get faster, because now you have 4, you can run, even though those brains are processing them at the same speed, you have 4 of them doing it. The problem is, like, a lot of programs aren't necessarily written to take advantage of that. And this is where we get into the idea of concurrency. Concurrency meaning being able to do things at the same time. A lot of programs use what's called multi-threaded concurrency, because what happens is that you might have that one core may have multiple jobs, and each job that it's doing is called a thread. Okay, and then each thread only can do one thing at a time. So what I can do is I can break up the job across multiple threads on one core. Okay, that's one way to handle concurrency. Or you can do what JavaScript does, where JavaScript is a single threaded, but it uses what's called an event loop. And it's just the way it organizes the to-do list of things to do, makes it feel like you're doing multiple things at the same time. And then there's basically multi-processor concurrency, where I'm not just saying, hey, let's have separate jobs on the same processor, but let me split up my job among different processors. Okay, and that's sort of like the big thing right now, kind of figure out how to create the abstractions in code to make it easier, because that's hard to coordinate, right? Because if you're a programmer and you say, okay, let me split up my job into different parts, well, this part of my job may depend on this thing happening first. This part of my job may depend on these two things happening first. So how can I split up my job across multiple cores and make sure that, like, hey, this job is not sitting around waiting for this job to finish, and that just ends up slowing things down anyways. And that's really hard. That's a really like a brain buster thing to think through. But those are the modern challenges nowadays to really help push hardware, current hardware, to its limits and speed. So hopefully this gives you a better perspective of just sort of like how computers work and sort of like what the terminology is and whatnot. At the end of the day, like, we're just writing programs for the computer to do things, but there is a whole world of like what's happening under the hood that if you at least have a high level appreciation, which was the goal of this video, it can help you think through like why you use particular tools and why certain practices are frowned upon or some practices are better. Why do we care about different like formats and things like that, and the differences between different languages when you think about high level and low level. Yeah, so hopefully you guys watch this. Again, this is not something where you watch once and you're going to absorb everything. You might want to watch this video 2 or 3 times periodically to kind of help get a refresher on this. But hopefully this lays some useful groundwork. My name is Alex Musset from alexmussetcoder.com. Have a great day and enjoy.